Dynamic lift. Dynamic lift is the force that acts on the body, such as airplane wing, a hydrofoil, or a spinning ball, by virtue of its motion through the fluid. Because of the motion of the body in the fluid, the dynamic lift, or we can say force, acts on the body. Why? When the body is moving in the fluid, what will happen? Some force is acting on this body because of its motion through the fluid, and this dynamic lift is the force that is acting on this kind of body. In many games such as cricket, tennis, baseball, or golf, when a spinning ball deviates from its parabolic trajectory and move through air, that is because of this dynamic lift. Okay. Now explain the spinning of the ball, or we can say explain with the help of Bernoulli's principle that why does a spinning ball follow a curved path during flight. Now see, ball moving without spinning. This is the first figure which is showing you the ball which is moving without spinning, and streamlines of the fluid are also shown, okay, around the ball. So this is the ball, and these are all the streamlines. In this figure, the streamlines around a non-spinning ball moving relative to the fluid. Okay, so non-spinning ball is moving relative to the fluid. It is clear that the velocity of the fluid above and below the ball at corresponding point is the same, resulting in zero pressure difference. So there is no pressure difference between the streamlines here above the ball and below the ball. So there is no pressure difference, so this ball will travel in this particular path without deviating, or it will go straight, we can see. Air exerts no upward or downward force on the ball in these circumstances. Okay. Now when the ball is curling or it is spinning, as a result, there is an upward force resulting in a dynamic lift of the wings, or we can say dynamic lift of the ball, we can say. Whenever it is curling, there will be a pressure difference. There is no curling or no spinning, there is no pressure difference. Then when the ball is moving with the spin, what will happen? There will be a pressure difference. Okay. In this figure, see, the ball is shown which is curling like this. Okay. A spinning ball drags air along with it. So air is dragged along with the spinning ball. If surface is rough, more air is dragged. Okay. The crowding of streamline at above the ball indicates high velocity and low pressure. So here the streamlines are crowded. You can see more streamlines in comparison to the place here below the ball. Okay. So more the streamlines, there will be high velocity, and there will be low pressure. So if there is low pressure, then here the pressure is high. Pressure is high compared to this particular place. So the ball will be not moving on straight path, but slightly it will drag this side, or on the upward direction, we can say. Or if you are throwing it in the, say, cricket, then either it will move right or left when it is moving straight. It will not go straight, but in air it will move slightly towards left or right in air. Okay. There are sparse streamline or less streamline below the ball, which indicates low velocity and high pressure. Okay. Here there will be a low velocity. Okay, and pressure is high. So what will happen? The ball will experience the force in this particular direction, resultant force will be in this direction, as it was moving in this particular direction, but as a result of this pressure difference it will experience the force in the upper direction according to this figure. Okay, thus difference in velocities of air result in the pressure difference between the lower and upper faces, and there is a net upward force on the ball, and because of this it will go, or it will tend to move towards the upper direction. This dynamic lift due to spinning is called the Magnus effect. Now we shall talk about the viscosity, that is stickiness, which is always there or associated with the fluid. Generally stickiness we have experienced that in the liquid. Okay, in a layer by layer flow, or we can say laminar flow, any two consecutive layer of the fluid behave, or they are having relative velocity between them. So one layer is having, say for example, the fluid is flowing layer by layer. This is the fluid which is flowing. Now try to understand the layer which is in contact with the ground, or we can say the surface on which the fluid is flowing. It is approximately stationary. The fluid which is flowing, okay, the lower layer is approximately stationary. Then as you move upward, the speeds of different layers are in the increasing order. So uppermost layer has highest speed. So these two consecutive layer, if you try to understand, these two consecutive layer if you try to understand, then there will be a relative velocity. Okay, and there will be the internal force of friction between these two consecutive layers, which is nothing but the viscous force. The property of the fluid due to which relative motion between two consecutive layers is known as viscosity of the fluid. This is the internal force or internal frictional force between two consecutive layers, and this internal force is a viscous force. That is the main crux of this particular topic. Now suppose a fluid like oil is enclosed between two glass plates as shown in this figure. Try to understand. There are two glass plates, okay, and here there is a oil between these two glass plates. Okay, the bottom plate is fixed with, while the top plate is moved with constant velocity v relative to the fixed plate. So what you are doing, you are having the velocity of the upper plate with respect to this stationary plate. Okay, stationary plate. With respect to this stationary plate, you are moving this upper plate with some velocity v. The fluid in contact with the surface has the same velocity as that of the surface. So here, whichever fluid which is in contact with this upper plate will have the same velocity as that of the plate. Okay, while try to understand the lower fluid or lower layers of the fluid. Okay, the fluid in contact with the surface has the same velocity as that of the surface. Hence, the layer of the fluid in contact with the top surface move with velocity v, and the layer of the liquid in contact with the fixed surface is stationary. So, there are two different layers if you try to understand. One is in contact with the upper glass plate, the other one is in contact with the lower glass plate. Now you are moving this particular glass plate, so the fluid in contact with the upper glass plate will move with some velocity. Rather, this layer of the fluid is not going to move, it will remain stationary. So there is a change or difference of velocity between the fluid which is in contact with the lower glass plate and the upper glass plate. This we can see with the activity. Okay. The velocity difference is v, we can say, okay, because lower layer is having 0 velocity, upper layer is having the velocity v, so the velocity difference is v. The velocities of different layer increases from bottom to top uniformly. Okay, now if you try to understand the layers in between the upper layer and lower layer, then this layer is having zero velocity, so the fluid in contact with this layer will have zero velocity. Now if you go on having the different layers, okay, if you are going in upward direction, then relatively the velocity is getting increased and maximum velocity is v, that of the layer which is in contact with the upper plate. Okay, that I have explained. You can see, say for example, you have a bottle which consists of honey. Okay, and if you are pouring the honey from the bottle, say you are making the bottle like this. Okay, now the honey will come out, but if you look at the layer which is in contact with the bottle at the bottom of this particular container or a bottle, then this layer in contact with the bottle is stationary. The fluid is coming out layer by layer, or we can say honey is coming out layer by layer. This is a practical experience that you can do at home. For any layer of liquid, its upper layer pulls it forward while the lower layer pulls it backward, or it tries to remain stationary. This results in the force between the layers. Okay, this type of flow is known as laminar flow. When a fluid is flowing in a pipe or a tube, then the velocity of the liquid layer along the axis of the tube is maximum. Now if you consider the flow in the bottle, then what I have explained that you can experience. Now if the fluid is flowing through the pipe, then the layer which is in contact, or layer which is there on the axis, will have the maximum velocity, while the layer which are going in the upper direction, okay, layer which is in contact with the tube will have zero velocity. Similarly, if you are going away from the axis, try to understand, if you are going away from the axis, the velocity of the layers are in decreasing order, or layer which is in contact with the pipe will have zero velocity. Okay, the velocity of the layer which is there at the axis will have the maximum velocity, which is shown here also in this figure to make it very clear. Okay, now coefficient of viscosity in context with the stress and strain. Now see, when the layers are moving, that of the liquid between the two plates of glass, we can understand this, that let the velocity of the upper layer is v. Now see, some distance travelled in say time interval delta t will be delta x, and that delta x is equal to v delta t. Okay, that is this distance travel. Okay, now during time the liquid has undergone a shear strain. Okay, shearing strain, there will be a change in shape, so there will be a shearing strain. Okay, and that shearing strain is nothing but delta x upon L. Okay, that is that we have studied in the previous chapter also, that if this angle is theta, that is change in shape. Okay, so tan theta is shearing strain, and that is opposite upon adjacent, and this opposite is nothing but say delta x, and adjacent line is having the length L. So that shearing strain will be delta x upon L. Okay, the strain in the flowing fluid increases with time continuously, because this delta x is changing with respect to time as the fluid is moving. Okay, or the upper glass plate is moving. In this case, stress depends on the change of strain or strain rate. So rate of change is taken delta x. Okay, it is delta x upon L, but it is taken as delta x upon L upon delta t, that is rate of change of shearing strain, or we can say it can be written as delta x upon L delta t. Now as you know, delta x upon delta t, delta x upon delta t is nothing but V. So V upon L can be the rate of change of strain. Okay, here shearing stress is force upon area. Shearing stress, as you know, it is F upon A, where A is the area of contact surface, F is the viscous force. Now coefficient of viscosity, coefficient of modulus or modulus of rigidity, we can say modulus of rigidity, here it is taken as coefficient of viscosity, that is shearing stress upon shearing strain. Now see, shearing stress is F upon A divided by shearing strain is V upon L. So we can say it is FL upon V into A, which is shown here in the first equation. Okay, or if you make this is equal to eta, that is coefficient of viscosity, which is pronounced as eta. So if you make the viscous force, here the force is a viscous force as a subject of formula, then the equation will be, okay, F is equal to eta A V upon L. Now try to understand, the upper layer is having velocity V, the lower layer is having velocity 0. So this difference of velocity is V. Okay, so difference of velocity divided by this L. L is nothing but the distance between these two layers. Sometimes it is taken as delta V by delta x also. Okay, and it is known as the velocity gradient. This V upon L sometimes is taken as velocity gradient. Okay, gradient, that is change in velocity per unit distance. Okay, SI unit of viscosity is Poiseuille. 1 Poiseuille is 1 Newton second per meter square or Pascal second. Okay, that is the unit of eta. Okay, CGS unit is 1 poise, sometimes it is taken as 1 poise, and 1 poise is 1 dyne second per centimeter square. Okay, 1 Poiseuille is 10 poise. Okay, 1 Poiseuille is 1 dyne per second per centimeter square, and 1 Poiseuille is 10 times the poise. The dimensional formula of coefficient of viscosity is m1 L minus 1 T minus 1. Generally, thin liquid like water, alcohol are less viscous than thick liquids like coal tar, blood, glycerin or honey. Okay, the viscosity of liquids decreases with temperature while increases in the case of gases. Try to understand, okay, this sentence. The viscosity of liquid decreases with temperature and viscosity of gases increases with increase in the temperature. Okay, there is a table in the textbook also which shows the viscosity at different temperature. Okay, thank you very much. Go through this topic 2-3 times. Okay, and try to understand.